Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS in Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation is the first in a limited educational webinar series titled REGENESIS Technical Perspectives on the application of advanced modeling for in situ groundwater treatment using colloidal activated carbon. This module in the series introduces the connection between PlumeStop and modeling and shows how designs can be explored and optimized. With that, I'd like to introduce our presenter for the series. We're pleased to have with us today Dr. Jeremy Bernstengel, Vice President of Environmental Technology at REGENESIS. Dr. Bernstengel serves as a senior REGENESIS technical resource on key remediation projects involving advanced in situ technologies worldwide. He is the author of the PlumeForce software used for design and modeling of the REGENESIS activated carbon-based technologies. Dr. Bernstengel received a Bachelor's of Science in Environmental Biology from the University of Essex and a PhD in Environmental Chemistry from the University of Lancaster. He is a Fellow of the Royal Society of Chemistry in the United Kingdom and a Chartered Environmentalist. He has over 30 years experience in the commercial and academic environmental sectors, including 20 years with REGENESIS. His creative and scientific insight have been recognized through 3 commercial patents. All right, so that concludes our introduction, and now I will hand things over to Dr. Jeremy Bernstengel to get us started.
Good. Well, thank you very much, Dane, for that introduction. As Dane mentioned, this is a series of 3 webinars looking at the practical use of modeling in the design and management of in situ groundwater treatment with colloidal activated carbon. This is module 1, which will focus on the principles of PlumeStop, colloidal activated carbon, how that segues with modeling and how that can be used in the design. Overall, this webinar series is about the use of modeling to expand our understanding of in situ activated carbon remediation projects. Modeling can offer a window into the governing processes behind the limited snapshots available to us through the point groundwater samples with which we'd be familiar as environmental professionals. The information that we can get through this can then be leveraged to improve design, improve performance tracking and projection, and to help support engineering management and project control. So within the series, webinar 1 will introduce the connection between PlumeStop and modeling and shows how designs can be explored and optimized. Webinar 2 will show how modeling can provide a window into hidden processes and shows why the mechanisms behind what we see may not be as they first appear. And then webinar 3 will explore how modeling can be used as a support tool throughout a project, assisting in communication, data interpretation, and performance optimization. So let's move on with this webinar, which is webinar 1, PlumeStop, colloidal activated carbon and modeling. We're going to look at the connection between PlumeStop and modeling and how designs can be explored and optimized. First, some basics, and I'll keep these simple. What is PlumeStop? What is a model? And how do we use them together? Well, what is PlumeStop? PlumeStop liquid activated carbon comprises tiny particles of activated carbon, 1 to 2 microns in diameter, in dispersion polymers. It has a surface area of about 1,000 square meters per gram. That's 100 acres per pound, and that's just the dry weight of the carbon, not the weight of the material itself as it would be shipped. This has a very high sorptivity. It is injectable at low pressure. it will flow like an ink, and like an ink, it will coat the flux channels that it passes through as a liquid and will attach to the soil surfaces. The coating that it leaves is small, and it does not impede groundwater flow to any measurable extent. This then gives us a powerful tool for plume management. The clue's in the name, plume and stop. But beyond that, there are a number of sophisticated applications for which the reagent can also be used. To give an idea of how it actually moves through the subsurface, this remains my favorite animation. And what we can see is PlumeStop being added to the column on the left, and powdered activated carbon, similar quantity, being added to the column on the right. We've looked at a time lapse over about 3 minutes, and we can see that the PlumeStop has just flooded down through the column, leaving a trail of black carbon on the soil behind it, whereas the activated carbon has plugged up at the top. So the activated carbon image on the right has kind of plugged, and what we can see is a sieve with a mesh size greater than the carbon particle sizes, the carbon not going through it on the right. On the left, we can see PlumeStop and the coating it's left behind. This image that you can see is sand particles prior to application of PlumeStop. If we look at the scale bar down here, we have a scale of about 50 microns. So these sand particles are perhaps 100 microns across. After the PlumeStop has been applied, note the scale bar is reduced to 20 microns, we can see the coating of activated carbon particles showing as this rough boulder field coating the top of the sand grains. That's kind of the coating that we would leave. And you can note that the macro pore spaces are hardly impacted by this. We've just got a coating on the surface. And that's why the impact to groundwater flow is negligible. How do we use PlumeStop? Well, let's look at a typical barrier configuration, and I'm going to keep this very simple for first base. This is the first webinar after all. We have an aquifer. Let's contaminate it with some dirty water. We're going to install a PlumeStop barrier. There it is, same coloration as we just saw in the sand column. That will behave more or less like a carbon filter, a Brita filter in the subsurface, so that when contaminated water passes through it, the water that comes out of the other side is clean. If we have biodegradable contaminants, then bioregeneration of absorption sites, or indeed ferroregeneration of absorption sites, if we use zero-valent iron and solvents, will extend the barrier longevity. The carbon quantity that we need for this is tiny. The groundwater flow is not appreciably affected. The capture efficiency is very high, which means that the contaminant advection, the contaminant movement in groundwater, is slowed significantly. The contaminants are slowed, the groundwater isn't. The groundwater may therefore flow through the barrier in days, but the contaminants may take years to pass through. And if they are amenable to degradation or zero-valent ion treatment, then applying reagents to support that into the barrier will extend its performance. And if the degradation rates are fast enough, the extension will be indefinite. What is a model? Well, a model can be thought of as rather like a flight simulator. It's a tool which will perform a complex set of interacting calculations for us, so that we can see how the system behaves when different inputs are adjusted. For example, we can use it to explore the impact of different reagent doses, different reagent mixes, or different reagent placement arrangements. And the software can then generate quantitative visualizations of the predicted outcomes of any of the scenarios that we've chosen to explore. Overall, therefore, this helps us with the 3 principles of understanding better, designing better, and communicating better. So PlumeStop and models, how do we use them together? PlumeStop lends itself very well to modeling. In simple terms, PlumeStop slows or stops a plume, plume and stop. Slowing a plume is known as retardation in the modeling vernacular, and retardation is common to all fate and transport models that may be available for looking at the fate and transport of contaminants in groundwater. Modeling can therefore provide insights into what PlumeStop will do. So let's look at the core principles of how this works and how this connection between PlumeStop and modeling takes place. The first thing to consider is that although PlumeStop is often considered a means of contaminant capture and is often described in those terms, this descriptor may well be a good starting point, but more accurately, what PlumeStop is doing is changing the equilibrium between phases. By the phases, I mean the soil phase and the groundwater phase principally. So in the image that we can see here, this is a schematic looking at dissolved phase contaminants in groundwater and sorbed phase contaminants on the soil. And the image that we can see on the left has what we would call a low KD. A KD is the equilibrium of soil concentration divided by water concentration. When the system is in balance and the rate of mass desorbing is the same as the mass sorbing, or in equilibrium, then the ratio of the concentrations we see in soil and groundwater is the KD. So we divide the soil concentration by the water concentration. So if this is our water concentration, high number, and this is our soil concentration, low number divided by a big number gives us a very low KD, and vice versa. If we have a low dissolved concentration and a high sorb concentration, we're going to have a high KD. I'm going to come back to the phrase KD again and again through this talk. Just recall that we're talking about the balance of mass, balance of concentrations on the dissolved or the sorbed phases. The equilibrium, the KD, is what will determine how much this plume is slowed. In other words, its retardation. So how does a barrier work? PlumeStop barriers will retard, slow the migration of a plume. Retardation is defined as the slowing of the plume relative to the flow of groundwater. And it occurs when some of the advancing contaminant attaches to the soil. So for example, if 1 part in 2 of the advancing plume attaches, then the plume velocity is reduced by half. Because retardation is caused by absorption of mobile dissolved contaminants onto the immobile soil particles, equilibration, retardation is therefore directly linked to the KD. And so the higher the KD, the greater the retardation. So in this image, we can see that most of the contaminant is in the dissolved phase and moves forward. And as it moves forward, only a small fraction attaches to the soil. The greater body moves forward with the groundwater, and so the slowing by loss onto the sorb phase is quite minimal. On the contrary, if we have a relatively small amount of mass in the groundwater compared to the amount that's going to sorb to the soil, then it's going to take an awful lot of plume flooding in to actually advance forwards if most of that mass is just nosediving onto the soil surface as we go. The higher the KD, the more attaches to the soil, the less moves forward, and the greater the retardation or the slowing of the plume. The degree of retardation is described by the retardation factor. Let's take a moment to look at retardation factors and complete the foundation to what I want to talk about in the rest of this presentation. A retardation factor determines, as I mentioned, how fast the contaminant moves relative to the groundwater. So if the retardation factor is 1, it's going to move at the groundwater velocity. So if this is a travel distance per unit time, the groundwater might move this far per unit time. Something with a retardation factor of 2 is going to move at half the groundwater velocity. Something with a retardation factor of 10 is going to move at 1/10 of the groundwater velocity. So when the groundwater's moved this far, depending on the retardation factor, the amount of movement is slowed significantly. What are some typical values that we might see in our industry? Well, for VOCs, chlorinated ethenes in soil, then we might typically have retardation factors in the range of about 1, vinyl chloride say, to 3, TCE say. That's on natural soil though. If we were to put a small amount of PlumeStop in that soil, 0.1%, and we have, let's say, 100 micrograms per litre of TCE coming in, we're not going to have a retardation factor of 3 anymore. We've changed the KD. We are going to have a retardation factor more like 600. And if that was a PFOA, for example, and let's say we've got the same amount of PlumeStop, 0.1%, and let's now say 100 nanograms per litre of PFOA, which would be more typical for mid-range PFOA plume, we might have a retardation factor of about 12,600. That means that the PFOA is going to move at 1/12,600th the distance that a groundwater plume will move in a given amount of time. This is for illustration only. I've used single species for these calculations, but you can get an idea of the scale of difference that we can make. PlumeStop and modeling. PlumeStop lends itself to modeling because retardation is a function of the sorbed-dissolved equilibrium, the KD. KD is fundamental to all fate and transport models. So therefore, if we can adjust the KD in any model, we can then explore what PlumeStop will do. Well, let's move on to an example. And for this example, I'm going to use the REMCLAW MD, REMCLAW matrix diffusion model. So REMCLAW stands for Remediation Evaluation Model for Chlorinated Solvents. The first version was produced by Ron Falter of Clemson University in South Carolina in about 2007, and it's recently been extended and updated with between Ron, GSI, and Kira Lynch of the EPA to accommodate matrix diffusion, which is a helpful addition. I've chosen REMCLAW because it's relatively recently produced. It's freely available. You can download it from the GSI's website, www.gsinv.com. And in my opinion, it's a nice piece of software. So fan mail to Shala, Ron, and the developers for the production of this. Thank you. In common with other off-the-shelf fate and transport software, it is not, I repeat, not designed for modeling activated carbon applications. But also in common with other fate and transport software, it can be used, or perhaps I should say abused, for this purpose. The outputs are not perfect, but nevertheless, they still do offer powerful insights into what an activated carbon application, what a PlumeStop application will do. Let's have a look at an example. So this is an example PFAS hack of REMCLAW MD. And REMCLAW is not set up for working with PFAS, but it can be hacked to do that. And the way I've done this is to set up the model for the subject aquifer as standard. You don't need to be able to read the details in the box, but these were some of the setup parameters that I used. But after this setup, I have then put PFAS parameters, sorption parameters, etc., into the slots that were really designed for the chlorinated solvents. I've therefore turned biodegradation off because PFAS don't biodegrade. And then I've entered the KD values manually. You can do this in this little box down here, Calc R in REMCLAW MD. The KD values to be put in can be calculated from the contaminant isotherm for activated carbon from whatever species that we're looking at. And the isotherms you can generally find from the literature. What is an isotherm, we may ask? An isotherm describes how the adsorbed concentration of a contaminant changes relative to the dissolved concentration of that solute at equilibrium. It's a mathematical description of that process. It can be plotted out, and in simple terms, the KD is then the ratio of the axis values of that isotherm plot at the groundwater concentration being modeled. So for example, if I was dealing with a concentration of whatever this point is for PFAS species number 1, then I can read from the isotherm or calculate from the isotherm what the sorbed equivalent sorb mass will be on the carbon at that point. And if I look at the ratio of those concentrations and do a bit of extra math, then I can work out what the actual KD is, really just correcting for the quantity of activated carbon in the system. So it's a reasonably simple approach. This calculation has to be done manually. It's not a part of REMCLAW MD. When I do it though, this is the type of thing I get. So this is an output from REMCLAW MD of my PFAS species after about 10 years. The graph is saying PCE, TCE, CIS, but the parameters I've put in are for PFOS, PFOA, and PFBS for this exercise. There's no activated carbon in there, there's just the natural fraction of organic carbon, the FOC, at about 0.1% of the soil mass. And we can see the concentrations of PFAS over this 100-foot distance declining. They're not declining because of degradation, they don't degrade. This, I believe, is a phenomenon of matrix diffusion. Types of KDs and retardation factors that we've got are the values that we can see here. If, however, and this is where the fun starts, I adjust the KDs to match those that we get with PlumeStop in the system, engineered KDs, and I'm using a fraction of activated carbon, PlumeStop, of about 0.2, a fifth of 1%, then you can see that the KDs and retardation factors are very different. Typically, we're going to be increasing them by 100 to 1,000 times. That's 2 to 3 orders of magnitude. And we can see in the image that the distance the plume has moved is very, very different. The plume has advanced maybe 250 to 1,800 feet under the natural setting, whereas with this PlumeStop addition, it's advanced less than 20 feet, in fact, less than about 5 feet for PFOA and PFOS. And this will tell us that maybe a 20-foot PlumeStop barrier at this application would contain these concentrations under that kind of seepage velocity, 220 feet per year, for about a 20-year period. It's a very simple exploration. It'll give an idea of scale. We can play around with it too. If I double the dose, we can see now that the fraction of activated carbon is about 0.004 rather than 0.002. Then the retardation factors are going to increase further, and the distance that the plume moves over the 10-year period is going to reduce. So at that higher dose, we could have a more compressed barrier. Perhaps we don't have space for a 20-foot barrier. Or indeed, by the same token, if we were to double the dose, we could, for a 20-year period, rather than a 10-year period, contain that PlumeStop. So we can play tunes with this. Double the dose, double the time, or double the dose, half the amount of distance the barrier has to cover for a given time. I trust you get the general feel of the types of play around we can do, even with some hacked software. RemChlorMD is just one example of what can be used. Similar hacks are possible with any model. The entry point might be different, but the principle is the same. The approach is well suited, I would say, to explorations with an existing model setup. If we perhaps have a model that's already been set up for a site that we're working on for some purpose or another, most of the setup work has been done. And the additional input adjustments, be it MT3D or whatever we're looking at, the additional input adjustments for PlumeStop are very small, and yet the output changes that we might see can be very significant. There's some fascinating explorations to be had there. There are limitations. Explorations using KD hacks to models are approximate only. The models were not designed for this, but the exercise is still informative. By all means, use it for aha moments to see how things behave. And indeed for semi-quantitative exploration, such as the ones that we looked at just a moment ago. Do not use the approach, however, for formal designs or for placing bets. The limitations are significant, but not so much that it makes the exercise worthless. The principal limitation that we have is that most existing models do not have a consideration for competitive sorption, and this makes a big difference. There are other limitations too, but competitive sorption is the most numerically significant. For this purpose, the PlumeForce modeling software was developed really to accommodate competitive sorption and to overcome some of the limitations of using off-the-shelf models for PlumeStop explorations, and to get to the point where modeling could be used for formal design. What is the PlumeForce modeling software? Well, it's proprietary modeling software developed by REGENESIS and operated by REGENESIS. I designed it and I started on it in perhaps 2016. That's what I looked like when I started, so you can get an idea about what the process will do to an individual. PlumeForce is a multi-phase finite difference model for the modelers among us that will accommodate dynamic sorption, destruction, and competitive interactions between target species themselves and between target species and non-target species. Practically, it will predict groundwater concentrations of the contaminants at any point in space and time in the modeled domain. And this has valuable uses at different stages of a project. It can be used in the early stages for conceptual site model refinement. It can help expose gaps or find out what the drivers are to what we might be seeing in a given plume or a given system. How significant is matrix diffusion, degradation, whatever else it may be. We can use it for design optimization. That's one of its main uses, to identify which reagents are best for a given setting, what type of dose do we need, and what might we expect from a given application scenario. And then we can use it as a performance yardstick to help with the tracking of a project once the PlumeStop application has been made, and we're looking at data coming in on month 1, month 2, year 1, year 2, and so on. How is performance tracking against the expectations? Is there any divergence? What does that divergence look like? We can use the modeling to help understand what that might be and how to get the project on track if there is divergence. That'll be the third webinar. Development of PlumeForce was specifically to support PlumeStop projects. The first version, as I mentioned, was developed in 2016. That accounted for sorption and biodegradation only, but there has been, well, 6-7 years of ongoing refinement and functionality and scope since that time. The key driver for its first development was to accommodate competitive sorption. This is not a feature of off-the-shelf fate and transport models, but it is a critical feature for activated carbon modeling. So let's take a look at what I mean by competitive sorption. This is pronounced on activated carbon, PlumeStop, but it is not pronounced on natural organic carbon, FOC. And for this reason, it's not in most fate and transport models, which are based around retardation on FOC, the fraction of organic carbon. And it is important because the sorption extent, the KD of each species, will change as the contaminant mix and the relative concentrations of contaminants in a mix change. These changes will occur through biological or abiotic ISCA transformations or the chromatic separation of contaminants within a barrier owing to differential retardation. Well, what on earth do I mean by chromatic separation or chromatographic separation? Well, for any analytical chemist among us, it'll almost be immediately apparent. The principle is the same as we would see in chromatography in an analytical laboratory. The process is something like this. Let's say we've got groundwater flowing in this direction. We have a continuous source of contaminants, and we have a mix of species. Species A is high sorbing, has a high KD. It therefore has a high retardation factor, as we've seen, and therefore it will have a low velocity V relative to the groundwater. Species B is medium sorbing, medium KD. Its retardation is therefore medium, and its velocity will then be medium. It's moving faster than species A. And likewise, species C, much lower sorbing, lower retardation, higher velocity. And so what we can immediately see is that naturally, the faster species are going to start to move ahead of the slower species. They may all start out together like marathon runners at the starting gun, but because they're all going at different speeds or different velocities, some way down the marathon course, then some are going to be arriving long before the others are going to arrive. And that means that whereas they might be bunched up in the beginning and there's lots of sorptive competition on the carbon within the barrier for them, as they progress through the barrier, that competition for the faster species reduces and reduces, and therefore the KDs are going to change, and therefore the velocities are going to change, and therefore the modeling outcome is going to be inaccurate if we don't take account of that. How significant is the change, perhaps you're asking? Well, let's take an example with some PFAS species, and I'm going to arbitrarily choose 3 species, 6,2 FTS as my high sorbing species, PFOA and PFBS as my species B and C. And what we can see here is that the retardation factors that we might have for a PlumeStop application of, let's say, 0.2% of the soil mass, all species at 50,000 nanograms per litre. That's quite hot. The retardation factors are going to be these that we see here. What's most significant is that as species B and C move away from the competition, you can see that their retardation factors increase significantly as they start to free themselves of the competition of other species. And you can see the lighter species, for example, at each step, its retardation is increasing by about 1/3. And so if we were to try and apply these concentrations that we see in a mix for the entire duration of the treatment, we would massively underestimate the retardation of the lighter species, and our modeling would be way off. That's the type of thing that would happen if we were to just measure isotherms with the source mix and then try and apply those isotherms to what's going to happen throughout the barrier. We're going to massively underestimate what's happening, especially for the faster moving species, which typically would be the critical ones for the breakthrough times of the barrier. Now, this is an example with just 3 species. A site's PFAS soup may contain thousands more than this, so the principle gets extended. The core PlumeForce functionality at the present time therefore includes the complexities of multiple reagents that we can add, different spatial arrangements and timing of the reagent additions, reagent consumption and longevity, but also the interplay of multiple competing species, whether they're the initial mixtures, whether they're parent-daughter cascades, or indeed the natural and hidden competitors, maybe not just the contaminant species that we're looking at, but the other stuff that may be in the mix as well. We can look at the interplay of multiple phases within the software as well. The mass that's in the high K transport units, by K I mean high conductivity transport units, mass that's in the lower K storage units, the silts and the clays rather than the sands or the gravels, mass that's sorbed to the natural organic carbon, the fraction of organic carbon, and mass that's sorbed to the PlumeStop carbon. Let's see how some of this works then in application. And for the rest of the slides I'd like to show you over the following 10 minutes, we're going to look at how applications can be explored at the design stage using PlumeForce. The first example that I'm going to look at is simple retardation, and I'm going to use TCE as my sample species. I'm going to keep it to 1 species to begin with and simple. And I'm simply going to look at the dose between retardation, between the PlumeStop dose and the longevity that we've got here. There'll be no degradation to begin with in this first example. So we're looking at TCE in an abiotic setting, maybe it's an aerobic aquifer, and PlumeStop only. So here are my settings in the box. Importantly, groundwater is about 225 feet per year. There's no degradation. There's a bit of matrix diffusion, and there's no degradation. The ambient biodegradation is turned off. We've got TCE coming in at about 1 milligram per litre, and it's flatlining over the distance that we're looking at because there's no interruption of the flow. We've got a constant source, and therefore the concentration is constant. On the vertical axis, we have concentration, and on the horizontal axis, we have distance. So this is like a longitudinal section along the center line of a plume. The source is somewhere to the left, and the plume is flowing off to the right through 10, 20, 30, 40 feet, and so on. Let's add a PlumeStop barrier, and we're going to make it an arbitrary 20-foot thickness. So in the model setup, it's from about the 10-foot point to about the 30-foot point, 20 feet overall in the direction of flow. The fraction of colloidal activated carbon, the PlumeStop application to the soil, is in this case a tiny amount, about a 1/100th of a percent of the PlumeStop, 0.0003 as a FCAC. I've deliberately made this small for the purpose of this exercise. That would be a very low dose for a real-world application. What we'll immediately see, this is time zero, what we'll immediately see after applying it is that the concentration in the application zone drops pretty much to non-detect. Even a small amount of carbon like this will be enough to sorb the TCE, probably down to detection limits or below. So we've immediately reduced the TCE in the application zone to non-detect. Down gradient, though, there is initially no change to the concentration because it takes time for the clean water to flow through the treatment zone and to flow down gradient, and the runtime is presently 0. So let's start to increase the runtime. A quarter of a year, 3 months. The clean water front has now started to move down gradient, and so we can see there's a bit of a clean space starting to appear, but the concentration decline is not instant because we're going to be getting some matrix back diffusion and desorption from the soil organics holding it up. As time moves forward, half a year, we can see the clean water zone starts to increase, back diffusion starts to tail off a bit, the concentrations drop, but we're starting to see a front of contaminated water beginning to make its way through the barrier. It's not out yet. We extend the time, 0.75 years, 1 year, all the time this front is moving forward as the clean water front is reducing. 1.25 years, 18 months, 1.75 years, and we've got clean water beyond the barrier, but now the mass has broken through at this tiny dose. So we've got, in this setting, less than 2 years longevity at a tiny dose. That's a small dose. What if we were to increase it? Well, let's try that. We can increase the longevity by increasing the PlumeStop dose. Let's do that. Initial application rate, these are the types of KDs and retardation factors that we've got within the barrier. This is out before the barrier, this is inside the barrier. We've got a retardation factor that's perhaps 13 times higher than background, but 13 times isn't really enough to buy us anything significant. So let's systematically increase the PlumeStop dose and see what happens to the longevity. We'll increase it bit by bit. So up to 0.2, we've now got 3.1 years longevity. We can see the KD and the retardation factor increasing. 0.04, up a bit more, 6 years. 0.06, about 9 years. 0.08, about 12 years to break through. 0.01, almost 15 years. 0.012, 18 years. 1.4, 20 years. That's enough for this design. So a fraction of colloidal activated carbon of 0.014 gives us 20 years of sorptive longevity. The retardation factor is now 435, which means the plume is advecting at about 1/435th of the groundwater velocity. The plume has taken 20 years to advance 20 feet. Without PlumeStop, it would have taken 40 days. It's been slowed by a factor of something like 200. That was sorption only, but TCE can degrade. So what if we combine that sorption with biodegradation? Let's take a look at some of the synergies of reagent applications. We're going to look at retardation coupled with biodegradation. So for example, we might be using PlumeStop, that's PlumeStop, with a compatible electron donor that we can co-apply with it, Aquafix, a long-lasting colloidal electron donor that's recently been released by REGENESIS to work simultaneously with PlumeStop. I'm going to take a look at biodegradation. Well, this is the same starting point that we had before, so no degradation, no interruption. And I'm going to start this exploration by looking at biodegradation on its own. So here is my electron donor application zone in a theoretic sense in PlumeForce. We'll model a 20-foot application zone and we'll allow in the software a 20-foot down gradient redox halo of donor influence where the treatment zone setup kind of segues back to ambient background. And with rates taken directly from the literature, I've used Aronson and Howard from 1997, maybe slightly faster in the case of vinyl chloride and ethene. This is the type of degradation that we might see. We can see the TCE flowing into the barrier And when it hits the barrier, it starts to degrade. Cis, DCE, and vinyl chlorides start to appear as daughter products. The cis breaks down into vinyl chloride, the vinyl chloride breaks down into ethene. And this process is not completed within the degradation zone. And so we're seeing some concentrations of the daughter products start to come out of the other side. Cis, DCE, vinyl chloride were not present to begin with, they're daughter products. I've set ambient degradation to 0, which is why these are flatlining outside. Under natural settings, there might be some slow degradation, but for illustration, we'll keep to the donor alone. So 3/4 reduction of TCE, okay, but now we've got a new 300 micrograms per liter of DCE and 75 micrograms per liter of vinyl chloride. Not good enough. Well, maybe these rates were too slow. Maybe we were a little bit cautious with these. What if the rates were actually double? Well, let's double them down to half of what they were. And this is what we see. Better, but we've still got quite substantial amounts of daughter products coming out of the barrier. Well, what if we extend the barrier zone? Let's double it from 20 to 40 feet. This is what we see. We've got now a 40-foot active biozone plus 20 feet of barrier. Getting better, but still not there. Okay, well, maybe the rates are a bit faster, or maybe that's a bit ambitious. Could I tweak them more? Yes, but I believe it. I'm not sure. So let's see what else we can do. Let's add some PlumeStop, and this is what we get. Here's some PlumeStop going in. It's a 20-foot barrier in this case. And what we can see is that the TCE and all the daughter products are entirely consumed within the first 3 feet of the barrier. And that's happening because we've suddenly brought an awful lot more retention time in the barrier to the flow of those contaminants, rather than flow through over a few days. The TCE would have taken years to go through, and that slowing has brought a lot more time for the degradation. And so within the first 3 feet or so of the barrier, we've got full completion. Well, that's great, Jeremy, but you didn't change the degradation rates. Are you sure that the same degradation rates would apply in a PlumeStop barrier? Well, let's have a look. Let's do a sensitivity test using the software of those degradation rates. What happens if we slow them down by an order of magnitude, let's say? This, by the way, we would have data on from a variety of studies, but I won't go into that in detail in this particular setting. So let's just do a sensitivity test and reduce the rates by 10. So we've got half-lives of 300 days for TCE and DCE, and 70 days or 35 days, a month or 2 months for vinyl chloride and ethene. And still, we can see that our contaminants of concern are consumed within the first 10 feet of the barrier. So that's pretty good. What about maybe not quite a slowed rate? Let's try about 5 times. We're slowed down. These are perhaps more reasonable rates to put in. We can see that we've still consumed our contaminants of concern within the first 5 feet of the barrier. We could therefore safely reduce the barrier dimensions to, let's say, 10 feet and still contain our plume. What that's done now is compress the treatment zone by greater than 75% compared to bio on its own. And there's still space in the barrier. Maybe we could relax the PlumeStop dose. Well, let's have a go at that. This is the dose we've got at the moment. If we relax it a little more, we'll see that the standing wave that we've got within the barrier can start to reduce a little bit as the PlumeStop dose is relaxed. 0012, it's extended a bit. 001, it's extended a bit more. 008, ethene is almost coming out of the barrier. 006, whoops, ethene's coming out. Vinyl chloride is almost on the cusp of coming out. That's probably a bit tight. So that's slightly relaxed too far, but it's given us an idea of the feel of things. We've got a better feeling of the dose-response relationship. Perhaps a fraction of colloidal activated carbon of 001 was about right. Let's put that back in. So there's our treatment zone at that dose, still compressed by greater than 75% compared to bio on its own. The footprint is now a lot smaller. It will fit into the space perhaps between a building and the site boundary. And the contaminant destruction is greater. even with a generous safety margin on the degradation rates. So what we've seen here is that the PlumeStop dose can be altered to increase the barrier longevity or reduce the required barrier footprint. We've seen a synergy between bioremediation. It could have equally been ferroremediation, ISCA, ZVI. PlumeStop will shrink the treatment footprint for the reagent use, and the reagents will reduce the PlumeStop requirements for that footprint and extend the treatment longevity. And we've seen how modeling can assist in the design process to help optimize the reagent combinations and to assist with the sensitivity testing of input parameters to work out what would be an appropriate but still appropriately conservative design for a given site. So these were examples using just two processes, sorption and bio, and sorption and bio in combination. As I mentioned, zero-valent iron alone or in combination could equally have been explored. What we did, I think, was enough for this talk. The permutations, as you might have fathomed, are endless, hence the benefit of modeling. PlumeStop, bio, ZVI, any combination, different doses, dimensions, placement arrangements, separate, overlapping, partially overlapping, combined, put in at different times, all of it can be modeled. This enables what-if scenarios can be explored and optimal design scenarios can be refined. But it's still only a simulation, perhaps we're thinking. How do we know it's right? Well, that's really dealt with through validation and calibration, which I'll look at very briefly so that we can keep to time here. This is done through comparing the predictions that we've made with the software to the observations that we get in the field post-application. And REGENESIS is very fortunate to see a lot of field performance, which enables us to calibrate the modeling to field performance rather than just trying to do what we can with test tubes and columns, etc. So what we do is we look at the predictions and we compare them to what's actually happened in the real world application. This provides validation and enables calibration of the model for that particular site. And so once we've got the calibration and we can see how numbers are actually tracking, then the estimated parameters in the model can be adjusted to match the actual field observations, and the model predictions for that site can then be refined. This will give us a better idea of the longevity of the performance or whether any adjustments might be necessary. And this can be done normally within the first few months post-application. The growing data set of observations that we get through doing this site after site, and even on the same site over time, but site after site, gives us a data bank of information that we can use to help improve future design predictions. And the assessment of the modeled predictions against field data also helps inform me what other refinements might be appropriate to improve the model and go for its continuous utility enhancement. So we're on about 50 minutes, let's wrap up. PlumeStop impacts can be modeled. This can be powerfully informative. Any model can be used for this up to a point. Activated carbon modeling requires consideration of competitive sorption. Modeling can support the remediation design processes, the exploration, the optimization, and the communication of what we might see. REGENESIS has a range of products that are compatible with PlumeStop that do not mess with the sorption. We have S-micro ZVI, an injectable colloidal sulfadated zero-valent iron, details on www.regenesis.com. We have Aquifix, an injectable colloidal long-lasting solid electron donor. We have ORC Advanced, slow-release dissolved oxygen source. It may be that the target contaminants are biodegradable aerobically. Perhaps we'd use another product, Petrofix, for that. But sometimes the target contaminants might not be degradable, but competing species might be. We might be dealing with, let's say, PFAS in a fire training area. Well, Rick McGregor of In Situ Remediation Services used ORC Advanced with PlumeStop on the first PFAS PlumeStop treatment to be formally written up in 2016. Do go and look at some of Rick McGregor's articles on his field experience with PlumeStop and PFAS. SMCDI and Aquafix can be co-applied with PlumeStop. This reduces the field work. Each is a powerful reagent in its own right, but compatibility allows the combined strengths to be leveraged and provides powerful synergistic opportunities benefiting overall project efficiency and performance. And the ability to model this in PlumeForce is essential to design and dose optimization. It also facilitates communication of the projected performance outcomes of the different design alternatives. So the PlumeForce software helps us understand better, design better, and communicate better. And with that, I'll close the first webinar. In the next webinar in this series, we're going to go a little deeper. We're going to go into the matrix and start to look at some emergent phenomena. There'll be some spooky surprises. We'll use modeling for X-ray vision, and we'll look at some calibrated examples of the utility of this. More formally, we're going to be looking at processes in isolation versus in combination, emergent phenomena, kinetic equilibria, when things look like they've stalled, but they certainly haven't stalled. We're going to look at the impacts of hidden mass and how we manage invisible things. And we're going to look at windows into hidden dynamics and how these impact project design. So with that, I'll close. My contact details are here. Thank you for tuning into this webinar. And at this point, I'd be happy to hand back to Dane to take a look at any of the questions that perhaps have come in through the course of this webinar. Thank you.
All right, thank you very much, Jeremy. So yes, as Jeremy mentioned, that's going to conclude the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's go ahead and circle back to the questions here. Jeremy, the first question is, can I get a copy of PlumeForce?
It is REGENESIS internal at the present time. So the answer is apologies, but no, you can't. But we do provide free support with it on projects.
Okay, thanks, Jeremy. So the next question here is, you mentioned that we can use other models. What other models can we use?
Well, really any subject to their intrinsic strengths and limitations, which the modeler would probably understand. Ideally, the one that you have set up for your site or project, or that you know best. Other than that, GSI's RemChlor MD is a good recent one that's freely available, as I mentioned in the talk. I've also used BioChlor over in England. I've used the Environment Agency's RTM model for level 3 groundwater. These can be illuminating, they can be good for explorations and demonstrations and first approximations, but they don't accommodate competitive interactions, as I mentioned, and they don't accommodate nonlinear isotherms like Freundlich or whatever you may put in. So if you do want to take the modeling further and keep it independent from REGENESIS, then you might want to consider bringing in an external modeler. Grant Carey, for example, of Pore Water Solutions in Ottawa in Canada, is an experienced modeler. And I mention him because he's written a number of publications on the modeling of PlumeStop in projects and certainly has a good deal of excellent experience to bring to bear.
All right, thank you, Jeremy. So here's another question, and the question is, how do you calculate the KD to put into another model?
Okay, that was buried in the webinar early on. Basically, you need to know the isotherm of the species that you're dealing with, and KD is the ratio of sorbed mass to dissolved mass at a given equilibrium concentration, then corrected for the amount of PlumeStop in the system, the FCAC that we've applied. In other words, the y-axis divided by the x value. The other options that you'd have, which may be easier from the get-go, is to simply tinker with the FOC term in the model, raise it by, say, 200 to 800 times, or indeed you could adjust the individual KOC values that you might have for your contaminants. And again, you'd increase those by 2 to 3 orders of magnitude, typically about 200 to 800 times. And that would give you an idea about how the performance would change on PlumeStop compared to the natural fraction of organic carbon, which you'd probably keep set in there at about 0.001.
Okay, thanks, Jeremy. So we have time for one or two more. This one is, you showed how competitive sorption makes a big difference. What about competition from other compounds you might not have analyzed for, natural organic matter, or the other 6,000 PFAS species as an example? How do you account for these?
That's a very good question. PlumeForce at the present time allows up to 22 named species to be modeled in parallel. And in addition to this, there's an allowance for competing organic matter to be put in there. On top of this, it's possible to enter a full spectrum of sculpted competition to account for best estimates of unknowns. I mean, that's almost a webinar in itself. How we make these estimates of what else is there is another story. But the software has the knobs and dials that enable us to account for a smaller or much greater body of other PFAS species of a range of different competing sorptivities and other unknowns. Even if we don't know what these unknowns are, and by definition we don't, the process enables sensitivity analysis and therefore a means of assessing and assisting in us to come up with some sensible engineering estimates. So we might not know exactly what the competition is, but we can take a few guesses at it and we can see how far that's going to throw the projected performance off. And that's what we've got to do as design engineers. We work with what we can. There are formal ways of going deeper than that, but that's a good start that can be done at the desktop level.
All right, thank you very much, Jeremy. So that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. Just a reminder that, as Jeremy mentioned, part 2 of this REGENESIS Technical Perspectives webinar series is coming up next week. This module will show how modeling can provide a window into hidden processes and why the mechanisms behind what we see may not be as they first appear. If you would like to learn more about remediation solutions from REGENESIS, please visit regenesis.com. Thanks again to Dr. Jeremy Bernstengel, and thanks to everyone who could join us. Have a great day.